In the previous lesson, we've talked about what semiconductors are and how the two basic types of semiconductors, that is the N and P types, are formed. We also discussed what happens if these two types were joined together, resulting to the diode. We discussed the current and voltage characteristics of the diode in the forward and reverse biased modes. In this lesson, we are going to discuss one of the most basic diode applications, as a rectifier in a power supply. Towards the end, you learn how to make a power supply. Let's review the current voltage characteristics of the diode, beginning with the ideal diode. In this circuit, we have a resistor in series with a diode. When the input voltage is forward biased, the diode allows current to pass through. The diode simply acts as a closed switch. In the reverse bias mode, when the input voltage is reversed, the diode does not allow any current to pass through. The diode in this case acts as an open switch. In the non-ideal case, or the practical model of a diode, the potential barrier of the diode is represented in the shaded region as a battery in the reverse bias configuration in relation to the input voltage in series with a closed switch. Thus, there is a voltage drop across the diode. In silicon, it is 0.7 volts, while in germanium, it is plus 0.4 volts. In the reverse bias mode, the orientation of the input voltage is reversed. There is no voltage drop across the diode, and the switch is open. In the previous two cases, we have not considered the internal resistance of the diode. Since the ions continuously interact with other ions, as well as with the intrinsic atoms, then there should be resistance arising from such interaction. In the complete diode model, this resistance is included as a slope. In the forward bias mode, the complete diode model includes a reverse bias diode voltage, the closed switch, and the internal resistance of the diode. It is called a dynamic resistance because the resistance changes with voltage. For now, you shouldn't worry too much about that. In the reverse bias mode, the diode is represented by an open switch in parallel with an internal resistance of the diode as a result of the reverse current. Because this resistance is extremely high, there's a very small reverse current present in the negative bias region of the IV curve. The slope that represents this negative resistance is evident in the figure. In reality, this slope is not actually evident as the reverse bias current that is present. Let's consider the simplest diode circuit with an AC source. The first diode circuit that we are going to discuss is a diode in series with a resistor. The input voltage is a sinusoidal AC voltage operating at a particular frequency. If the output voltage is taken across the resistor R1, how will that output voltage look like? If we take an oscilloscope and measure the voltage across the input voltage, we will get the black curve. The black curve is not seen in the positive portion of the voltage or the forward bias portion, since it is superimposed by the red curve. With an ideal diode, the turn-on voltage is at 0 volts. This means that as soon as the input voltage reaches 0 volts going to the forward bias, the diode will give an output current. Without the resistor, the current would be infinite. With the resistor, the current would be V1 over R1. So the output voltage just follows the input voltage exactly. On the other hand, if the diode is non-ideal, the diode only allows current to pass through when the input voltage is at positive 0.7 volts. There's always a voltage drop across the diode of 0.7 volts. This is why there's a difference between the blue curve and the black or red curve. Thus, the output voltage is just the input voltage minus 0.7 volts. In the negative portion of the voltage, or in the negative bias region, the diode does not allow the passage of current. Thus, the output voltage is 0 as long as the input voltage is below plus 0.7 volts. This is why you only see the black curve, which is the representation of the input voltage. You must keep in mind that we are measuring the peak voltage and that all calculations refer to the peak voltage of the input voltage. As you can see, we only have an output voltage in the forward bias region and not in the reverse bias region. This type of behavior is called rectification, and this circuit is called a half-wave rectifier. When the orientation of the diode is reversed, then in the forward bias region, there is no current. In the negative region of the voltage or in the reverse bias mode, the diode allows the passage of the current. Thus, current is present when voltage is negative. This evidenced by the red and blue curves in the figure, which represents the output from an ideal diode versus the non-ideal diode or complete diode respectively. The amplitude of the voltage is the same as in the other half-wave rectifier, except that the voltage is negative. We can create a circuit that outputs a positive sinusoidal signal regardless of the sign of the input signal. Such circuit is called the center-tapped full-wave rectifier. To achieve this, we first connect a transformer at the input voltage. A transformer is just two inductors connected in parallel and that are not in contact with each other. The inductor that is connected to the input voltage is called the primary coil. The inductor that is connected to the remainder of the circuit is called the secondary coil. If current goes through the first inductor, current in the other inductor is induced according to Faraday's law. The ratio of the voltages across the primary and secondary coils depends on the relative number of the coils between the two inductors. This is quite easily seen from Faraday's law. If the ratio of the number of turns of the primary to the secondary coil is, for example, 2:1, then the voltage across primary to the secondary is 2:1 as well. This means that the voltage is half. This type of transformer is called a step-down transformer. On the other hand, if the ratio of the number of turns of the primary to the secondary coil is, for example, 1:2, then the voltage across the primary to the secondary is 1:2 as well. This means that the voltage is multiplied by 2. This type of transformer is called a step-up transformer. In a full-wave rectifier circuit such as this, the transformer used is typically a step-down transformer. Since the source voltage is from a 220-volt source with a frequency of 60 Hz in the Philippines, the voltage has to step down for practical applications. A typical voltage used for practical applications is 12 volts. Thus, the turns-coil ratio is 220:12. Now that we understand what the transformer does, let's go to the two diodes. In the voltage versus time graph, we refer to the input voltage to the diodes as the output voltage across the secondary coil. In the first half of the cycle of the input voltage, we can represent the direction of the current as the red arrows. This direction is clockwise. Thus, the diode D1 is forward bias, while the diode D2 is reverse bias. Diode D1 has a voltage drop of plus 0.7 volts. The current, being not able to go to D2 because of the potential barrier, goes to R1. If the output voltage is measured across R1, then the result is the red curve as shown in the graph. For the second cycle in the negative cycle, the direction of the current is represented by the blue arrows. Now diode D2 is forward biased and diode D1 is reverse biased. No current passes through D1 and goes instead through. The direction of the current through R1 is the same as its direction in the positive cycle. The result is the red curve in the second cycle as shown in the graph. Thus, regardless of the direction of the input current, the voltage R1 is always positive. The difference between the input voltage, black curve, and the voltage across R1, red curve, is plus 0.7 volts, which is just the diode voltage. If we talk about voltage magnitudes, we can summarize it in this way. Across the input voltage, if it is an output voltage, it is 310 volts with a frequency of 60 Hz. This 310 volts is the peak voltage or the maximum amplitude of the input sinusoidal voltage. If you use a multimeter, you'll measure 220 volts. That is an RMS or root mean square voltage. It is related to the peak voltage by a factor of square root of 2. At the primary coil, it is still 220 volts, 60 Hz. At the secondary coil, if the turns ratio is 220:12, then the voltage across the secondary coil is 12 volts, and the frequency is still 60 Hz. In a transformer, this is an RMS voltage as well. The peak voltage is 17 volts. Since at any cycle current passes through only one diode, the RMS voltage after the diode is 12 minus 0.7 volts or 11.3 volts. Thus, the voltage across the resistor is 11.3 volts. Again, it is an RMS voltage. In addition, notice the wavelength of the red curve is halved compared to the black curve, or its frequency increases by 2 from 60 Hz to 120 Hz. Another type of bridge rectifier is the full-wave bridge rectifier. It is more commonly used in circuits compared to the center tap rectifier. Just like in the center tap rectifier, the input peak voltage V1 is stepped down by the transformer according to the turns ratio N. During the positive cycle, the current travels from the upper branch of the secondary coil to junction 2. The current then goes from junction 2 to junction 1 and not to junction 4 because diode D24 prevents the passage of current. From point 1, it goes to the ground and then appears at the other ground terminal going to junction 4. It then goes to junction 3 across diode D34 and then goes back to the lower branch of the secondary coil. Thus, the current passes through two diodes and therefore the peak voltage is reduced by 1.4 volts. During the negative cycle, the current travels from the lower branch of the secondary coil to junction 3. The current goes to junction 1 through diode D13 and not to junction 4. From junction 1, it goes through the resistor towards the ground and back from the other ground terminal towards junction 4. It then goes to junction 2 through diode D24 and then back up to the upper branch of the secondary coil. The direction of the current through the resistor is the same in both cycles and thus is always positive. In this circuit, the resistor is the bridge. One branch of the bridge circuit contains the series diodes D24 and D12, while the other branch contains diodes D34 and D13. Instead of a resistor, let's consider using a capacitor and measure the output voltage across it. At the first quarter of the cycle, the capacitor charges as the input voltage supplies energy to it. In other words, the output voltage simply follows the input voltage with a magnitude that is just different by plus 0.7 volts. This is shown in figure 40A. At the second quarter of the cycle, the input voltage decreases sinusoidally. The capacitor then charges slowly as shown in figure 40B. It continues to discharge slowly and provides an output voltage until the first quarter cycle of the second sinusoidal wave when the capacitor begins to charge again as shown in figure 40C. This behavior repeats for every sinusoidal cycle. The total effect would be what is called a ripple voltage. The ripple voltage results from the charging and discharging of the response of the capacitor to the input sinusoidal voltage. What the capacitor does is to filter out sinusoidal signal and essentially flattens out the voltage. However, it's still not completely flat and has some small ripples. The smaller the ripple, the more effective the filtering. Thus, the choice of the capacitor value is crucial to the filtering effect. Figure 41 shows the difference between the two signals and that has a greater ripple and a smaller ripple as a result of poor and good filtering. If the capacitor is connected to a full wave rectifier, then the ripple voltage is a bit smoother as seen in figure 42. This is the reason for choosing a full wave rectifier over a half wave rectifier. The ripple voltage is characterized by a ripple factor, which is the ratio of the ripple voltage to the average DC voltage. These parameters are shown in figure 43. Thus, what you want to achieve is a small ripple factor. We can derive an expression for the ripple voltage in terms of the input peak voltage, measured at the input of the primary coil of the capacitor. We begin with the expression for the charging of the capacitor in terms of the exponential function. For small ripples, this exponential function is approximated to its first two terms. Thus, between peaks, the ripple voltage can be approximated as Vp in times T divided by Rc, where T is the time between peaks. If the input voltage is 220 volts at 60 Hz, can you guess correctly what value of T you are going to use? You can directly compute for the RMS ripple voltage from this expression simply by dividing Vp in by 2 and then by the square root of 2. The factor of 1/2 is inherent in the RMS equation. The square root of 2 is obtained by taking the root mean square of the sinusoidal function. The mean is understood to be an integration over an infinite number of cycles. However, since the ripple function is not really a sinusoidal function, the RMS result is actually square root of 3. I have included a link in this topic's suggested links describing and showing this calculation. Feel free to take a look at it. You can also solve for the DC voltage since it is equal to the input peak voltage minus half the ripple voltage. This should be evident in the figure. In practical applications, the ripple voltage will always be evident. In order to smoothen out the ripples, a regulator is used. One of the ways to do it is to use a Zener diode with a transistor. Since we haven't tackled both Zener diode and transistors yet, I will refer you to a standard integrated circuit or IC regulator called the 7800 series regulator. This series comes in output voltages of 5 volts to 24 volts, which you can determine from the last two digits of its type number as shown in the figure. The IC regulator is a 3-terminal device that gives out a fixed output voltage. Oftentimes, a large value capacitor is placed before the input of the regulator for good signal filtration, and a second smaller value capacitor at the output of the regulator to improve transient response or stability. You can use a negative voltage output regulator by using the 7900 series instead. All of these regulators supply 1 ampere of current to the load and can hold the voltage output quite stably despite the changes to the input or output load. They also require a heat sink since they can get pretty hot during operation. Combining everything that we've learned with diodes, we can now build a power supply. Figure 45 shows an example of a basic circuit of a plus 5 volt regulated power supply. At the leftmost part of the figure, you can see the schematic representation of a power cord that is also grounded. A switch SW1 is present and connected along one branch of the circuit. The fuse F1 is also connected in series with the switch. This prevents any surge in current greater than 0.1 amperes, according to the figure, by breaking the filament in the fuse when the current exceeds 0.1 amperes. The transformer T1 is a step-down transformer from 120 volts AC to 12.6 volts AC. The bridge rectifier is used in this schematic. The filtered output is seen across capacitor C1, which is also the input to the regulator. The regulator is a 7805 which provides a 1 ampere plus 5 volt output. The capacitor C2 is connected to the output of the regulator directly to the ground to stabilize the signal better. If you wish to have an adjustable output power supply, you can use an adjustable regulator such as the LM117, LM317 series for positive output regulators, or the LM137 and LM337 series for the negative output regulators. The output is set by the resistors R1 and R2. R2 is a variable resistor. Now that you know how to make your own power supply, you can already start designing your own power supply for your own needs. You've seen that the core of converting an AC signal to a DC signal is the rectifier. The filters and the regulators only serve to smoothen out the signal. In the next video, we'll discuss other types of diodes and their applications. See you then!